All right, Chapter 2. You know Rene Descartes? Famous French philosopher dude. You might remember his famous statement of, I think, therefore I am. Well, he was a mathematician, old school, back in the 1600s, and back then they didn't have modern conveniences. Europe had imported algebra from the Arabic world, and we had geometry from the Greeks. So in algebra, they would study quantities and how you could put them together to balance equations, and in geometry, they could study things like triangles and pentagons. That's a hexagon, but no one had thought to put them together at this point, till Rene Descartes. So back in the 1600s, honestly, algebra was really inconvenient because we didn't have modern conveniences like 7x plus 2 equals 3x plus 4 to try to solve. Back then, it was all written out in complete sentences in Latin. So let me translate to English. You'd have to say something like, 7 times the unknown quantity, with 2 added to it, is equal to thrice the quantity plus 4. What is the unknown quantity? And then you'd sit there for half a day trying to piece that out in English, well, Latin really, before you could get your answer. Meanwhile, geometry, everything was done with a straight edge and compass. What shapes can we construct? How do these two fit together? I don't know. Now, Rene Descartes was he was on the cutting edge of mathematics, so he was solving problems like brachistochrone. These were the unsolved problems of his day. Believe it or not, there are still math problems that aren't solved, but these were the problems that everyone was trying to solve. First person to solve these was going to be real famous. Brachistochrone was, is there a curve such that no matter where on the curve you set a rolling ball, by the time it reaches the bottom of the curve, exactly the same amount of time has elapsed? You might be thinking that's impossible. Wouldn't the top one take longer than the bottom? Well, look at it this way. This bottom ball is just going to meander down, whereas this top ball is going to pick up a lot of speed real quick. They're actually going to reach the bottom at exactly the same point if you can build a brachistochrone. It's more of a toy than anything, but mathematicians were having a lot of trouble solving it back then. Or here's another problem. The catenary. If I mount a chain to 2 points, what exactly is this U shape that it hangs in? Now, I know what you're thinking, and the answer is no, it is not a parabola. It's some other shape. Or how about conic sections? Cone, I think of it as a party hat. The idea is that if we take a knife and we cut it straight, what kind of shapes can that intersect the cone in? Turns out there's 5 of them, and if you can solve the problem of conic sections, that involves naming all 5 and giving equations from them. But no one had done that yet, because these were clearly geometry problems, so they were trying to solve them with a pencil and straight edge, and that just wasn't cutting it. Now, Descartes, what he would do is he would lay in bed, sometimes till 11 a.m. or noon, just like us during quarantine, am I right? So he'd just lay in bed and think about life. Think about the world, think about these unsolved math problems, what can we do? And one day, while Descartes was laying in bed, there was a little fly in his room. Now that fly was flying around here. Oh, that motion is not at all smooth on the recording, is it? Well, let me just go ahead and put him on the ceiling here. Descartes was thinking about how to solve a geometry problem with some kind of algebra, put numbers to a geometry problem in a sane way. And this fly got him thinking, if he were going to try to describe the position of the fly to a friend, he might say, well, this fly is 2 ceiling tiles away from the bottom of the room, and it's 3 ceiling tiles away from the left side of the room. So if we were to start here and describe its position, we might say it's 3 to the right and 2 up. And just like that, he had it. With two numbers, he could describe the position of the fly no matter where it was on this plane. Like, this blue fly would be 6 tiles to the right and 3 tiles up from the bottom. Two numbers is necessary and sufficient to describe position on a, well, we call it now a two-dimensional plane. That two-dimensional doesn't make sense until you have Descartes' invention right here, but we think of these two numbers that describe the position, how far up it is and how far to the right it is, as being two independent dimensions that completely describe your location on this plane. And this is the foundation for everything from computer graphics, what pixel on the screen I'm going to select, to GPS, where on the planet are you? And it was all invented right here back in the early 1600s by a man who did not want to get out of bed. And so he thought to himself, well, by goodness, if I can do that, all of these math problems, I can put what came to be called the Cartesian plane over top of them. And I can say, how does this point and this point and this point, how do they relate to each other? What shape can I trace out if I label all of these points on a graph? What shape do I get if I call this cutting plane my coordinate system? What shape is this in that plane? And within a year, he had solved all three problems and become famous in Europe. So let's take a closer look at his invention, this Cartesian plane. This is not just a place to solve. This is it is when you have a graphing calculator and you draw a graph. This is the graph. This is where you're drawing that graph. This is that two-dimensional plane. But it's way, way more than just a place to draw pictures. This is the meeting place of two different ancient branches of mathematics. The algebra of the Arabians and the geometry of the Greeks had never come together until Descartes' invention in bed while he was being lazy. See, some mathematicians will tell you laziness is a virtue because it leads to more clever solutions to do less work, and I'm one of them. So, lazy Descartes was able to invent this thing. Well, let's take a look at how it works here. We're going to have to start describing the position of the fly somehow. It's to the right and up from what? We'll call that point the origin. So if I go 3 units to the right and 2 units up, I have my starting point, the origin, and now I'm talking about a specific point. We'll call this 3, how many units to the right we go, and then 2, how many units up we go. These vertical and horizontal lines that I've drawn to kind of give me an idea of where I am in space, give me lines to plot along. These are called the x-axis and the y-axis. Whoop, did it twice. Can't spell axis. I don't know why we picked x and y, but so when I say how far right I'm going, a lot of times we're going to end up calling that number the x coordinate. And when I say how far up I'm going, we'll call that number the y coordinate. A lot of terminology, a lot of anatomy around this thing, right? Let's see. But that's enough terminology for now. So if I want to go 1 unit to the right and 5 units up, like 1 to the right and 5 up, that would be the point. We'll call that the point 1, 5. So it's 1 to the right and 5 up. Now what if I want this point? It's 3 units to the left and 3 units up. Well, really, going 3 units to the left, imagine I'm facing to the right, and I step backwards 3 times. I'll end up 3 units to the left. So really, 3 units to the left is the same as negative 3 units to the right. Make sense? So this is the point negative 3, 3. And if I wanted, say, this point, 6 units to the right and 2 units down, I'd call that 6, negative 2. Because 2 steps backward is the same as negative 2 steps forward is the idea. So that's how we plot points in the Cartesian plane. Heck, let's do one more. 2 more. If I go 2 units up, but I don't go any units left or right, I'll just write that down. I didn't go left or right, 0 units, but I went 2 units up. That means this point right here, the origin, is at 0, 0. So that's how you plot points on the Cartesian plane. Fairly self-evident. One other thing is that these axes, they kind of naturally separate the thing into four quarters. We're going to call them quadrants. And for whatever reason, we go counterclockwise. The quadrant where both things are positive, both coordinates are positive, we're going to call that quadrant 1. Then we're going to go counterclockwise around, like clock but backwards, right? So this is quadrant 2, 3, and 4. These are Roman numerals. That'll show up a lot more if you take pre-calculus or trigonometry here. You'll be using those 4 quadrants heavily. In this class, we don't talk about them much, but probably good to have the terminology just in case we want to refer to those broad areas of the graph. So we got our quadrants. I told you this is the place where we do draw pictures of graphs, but it's so much more than that. It's the meeting place of algebra and geometry. And what that means is, if I know how an object looks on the Cartesian plane, I can usually deduce some information about its algebra, and vice versa. In fact, a graph of a function or an equation for the function, either one is a complete description. So they're redundant in a way, and what that means is we have symmetry between them. We're going to do that a whole lot this semester, an amazing amount of using geometric information to glean algebraic information and vice versa. It's going to be real nice, is what it's going to be. Let's do our first little bit. So I told you I call the up and down the y coordinate and the left and right the x coordinate. If I write a relationship between an x coordinate and a y coordinate, for example, y equals 2x plus 1, I'm saying this equation, in algebra, this is just an equation. It's a relationship between variables named x and y. But if I identify those with the left and right coordinate and the up and down coordinate on the Cartesian plane, I can call this a relationship between the x coordinate and the y coordinate of some points. What I'm going to say is this equation describes any point where no matter what the x coordinate is, the y coordinate is twice that plus 1. Now, back in Descartes' time, they would have to talk about that with complete words. The invention of algebra as we know it, the modern notation, didn't come until later. I believe that was Gauss's invention in the 1700s, but it's the same idea. It describes all points of the form x comma 2x plus 1. So let's take a look at what that means. I'm going to grab some different values of x, like maybe -2, -1, 0, 1, and 2, and see what values of y would put a point on the plane, put a point in this relationship. So y is always 2 times x plus 1. So 2 times -2 plus 1 would get us a -3. 2 times -1 plus 1 would get us a -1. 2 times 0 is 0, plus 1 is 1. I think you see the pattern. We're going to get a 3 here and a 5 here. So this equation describes all of these points and so many more. Let's go to the Cartesian plane and plot each of these points. See if we can understand what this equation is trying to tell us. -2, -3. So we'll go 2 to the left and 3 down. That's the first point. -1, -1. 1 to the left and 1 down. No distance left or right, but 1 up. This is the point 0, 1. 1 to the right and 3 up. Can do. 2 to the right and 5 up. You see in the pattern? All of these points lie on a straight line. In fact, if I fill in the pattern your brain's already trying to tell you is there, this really is what this equation describes. So written algebraically, it's the object y equals 2x plus 1. It's an equation that relates x and y together. But geometrically, it's a straight line, one straight line on the Cartesian plane. And the idea is that these are just 2 different ways to write exactly the same mathematical object. Both of these boxes are complete descriptions of this mathematical object. It is both a line and an equation. And that duality is what the Cartesian plane gets us. So what that means is I can take any property of the graph over here and say that tells me something about how this equation behaves, and vice versa. For example, notice that this line, we say it has a slope. We'll talk about slope more next section, but remember the slope is rise over run. This thing has a slope of 2, which means it's kind of going steeply upward. Every time we go 1 to the right, we go 2 up, 1 to the right and 2 up, 1 to the right and 2 up. And over here, the coefficient on x is 2, and somehow that's the same piece of information, but related to us through 2 different media. Okay? So this convergence of these 2 kinds of information is going to get us so much, it's going to do so much useful work for us this semester. So I cannot emphasize enough how important this Cartesian plane is to us because of that convergence. All right. So that's how you get a graph of an equation. We call this the graph and this the equation, if you want. So this is the graph of this equation. It's the set of all points in the Cartesian plane, x comma y. It's every point x, y, where they satisfy this equation, where y is 2 times this number plus 1. So numbers like 0, 1, 1 is 2 zeros plus 1, 1, 3, 2, 5, and -1, -1, -2, -3. There are actually infinitely many points that satisfy this equation. So I could have x is 2 or 3 or 4 or 5 or 6 all the way up. And there's points in between here. I could have x is 1.5. That would make y 1 3/4. Nah, that can't be right. 1.5. Sorry. If x was 1.5, that would make y equal to 4, wouldn't it? 1.54. Or if x was 1 3/4, y would be 4.5, and so on. There's between any 2 points is another point. We call that a continuum whenever you have that property. So there's infinitely many points. There are a huge number of points on this line, and they all satisfy this equation. If a point isn't on the line, like 0, 5, well, 5 isn't 2 times 0 plus 1. If it doesn't satisfy the equation, then it's not on the line, and vice versa. So a point is on the line if and only if it satisfies this equation. That's what we mean when we say that this is the graph of the equation. That's a real important point. So then, let's see, what's some other interesting things we can do with the Cartesian plane? Some first bits. Let me plot another equation. What if I had y equals x squared minus 4? Right. Make my table again, x, y. I'm gonna do a couple more points this time. Let's grab 7 different x values. -3, -2, -1, 0, 1, 2, 3. I'm just picking these arbitrarily. I picked all whole numbers. Of course, not every point on the Cartesian plane has a whole numbered coordinate. Most of them don't, but I pick whole numbers just because they're easy to compute, and my brain can fill in the gaps pretty easy. So let's see. -3 squared, be careful here, that's a positive 9. Minus 4 is 5. Got it? You square a negative number, you get a positive answer. So this one right here is 4 minus 4. This one here is 1 minus 4, 0 minus 4, right? This is 0, -3, -4, and 1 minus 4, 4 minus 4. These values are actually repeating themselves. 9 minus 4, so this is -3, 0, and 5 again. Got kind of a boomerang effect going. Graph actually looks like a boomerang. Let's plot these points. We got -3 and +3 both give us a 5 as the output. We got if x is -2 or +2, we're going to go up. Oh, none at all, huh? We're going to be right on the axis here. So that's -2, and 2. If we put a -1, we're going to be at -3. My axis isn't very straight there. That's not good. And if I put in a 0, whoops, did not mean to erase that. Here's the point, 0, -4. So these are the 7 points. Matter of fact, this thing even looks like a boomerang. I connect the dots. It's this kind of U-shaped curve here. We get this U-shaped curve anytime the largest power of x. Anytime we have a polynomial of degree 2, we call that a quadratic. We call this graph a parabola. We are going to study quadratics and their parabolas extensively this semester. This is just a first glimpse. Let's see here. A couple of things that a lot of graphs have are what we call an x-intercept and a y-intercept. So these folks right here are x-intercepts. They're where the graph touches the x-axis. Over on the equation, they correspond to what values of x you can plug in to get y equal to 0. The y-intercept is exactly the opposite. It's what values of y you can plug in to get x equal to 0. In this case, so we call that the y-intercept because it touches the y-axis. When we define functions in a little bit, you're going to notice you can have multiple x-intercepts, but for a function, whatever that is, I'll tell you soon, you can only ever have one y-intercept. And that's not every graph ever, but if it's a graph of a function, which are our main objects of study this semester, that's how it's going to be. So that's x and y intercepts. That's how we graph. Later, we'll learn more sophisticated methods to graph, so we don't have to plot points every time. No, they'll be very sophisticated. They'll get us a lot of cool techniques, but until then, this is what we're stuck with. So let's see. I have a couple more things I want to show you here in section 2.1. I want to show you the distance formula and the midpoint formula. It's good stuff. Let's do distance formula first. What I mean by this is if I draw 2 points in the plane and I hold a ruler up to them, how far apart are they going to be? Turns out there's an equation. We can turn that geometry back into an equation. This is one of the first things that René Descartes discovered when he made this thing, is this distance formula. Well, here's how it works. Let's say I have the points, I don't know, 1, 4, and 6, 4. How far apart would you say those guys are? Think about it for a second. We hold up a ruler, it's going to be perfectly horizontal. We don't go up or down at all. But this distance, it's 5 units, right? If I wanted to be fancy, I could say the reason it's 5 is 6 minus 1. I know that's so intuitive that it almost doesn't need to be said, but honestly, a deeper understanding of mathematics comes when you go and look at the things that feel so intuitive that they don't need to be said. Why are they intuitive? That's a question about the foundations of mathematics. Where does that intuition come from? Here, it's a 5 because we started at 1 and got to 6, so it's 6 minus 1 is 5. So the distance is the difference between those two coordinates, okay? And if this was a 6 and this was a 1, the distance would still be 5 because distance is always positive. Distance is always positive, so we're not going to ever put a minus sign on distance. So those are 5 apart. If this is the point, what is this? -2, 1, and this is the point, -2, -3. Those are right up and down from each other. Those are, well, what's 1 minus -3? It's 4 units apart. So same thing. You go down 1, 2, 3, 4. Oh, it's amazing. Looking at the foundations of mathematics and of our intuition, it's just a rabbit hole. You can keep getting more and more basic until you're at the level of trying to prove prove that 1 plus 1 equals 2. We've all been taking it for granted. How do we prove that? What do we use to prove that? What's more basic than that fact? Well, we can find some things. Or prove that a set contains all the elements it contains. Now, that's a real doozy. It sounds like it should be self-evident, but, man. They really went nuts. Look up Gödel's incompleteness theorem sometime if you want a real can't say that word in class. Mind blowing experience. Probably guess what I wanted to say, but all right. So that distance is 5. That distance is 4. That's pretty easy because they're horizontal from each other or vertical from each other. But if I end up in a situation like this, let's say this is the point 2, 1, and let's make this point, geez, how about 6? Yeah, 6, 4. That'll work. I have something in mind here. If I hold up a ruler, how many inches is the ruler going to say those are apart? What can I do here? Now, right now we got kind of algebraic facts. What Descartes realized is we could take this back to geometry. This is the oldest theorem we're ever going to use in this class, okay? This is due to Pythagoras. And he was working back in 2500 BC. So this is this is what, 4,500 years ago? This is way, way old. This is before Rome. This is before just about anything that we consider modern history. Pythagoras realized that if this side was called A and this was B and this was C, that A squared plus B squared equals C squared. Or as he would have put it, well, that'd be Greek to me, but let's translate to English. He would have said, a square triangle, the sum of the squares of the two legs will equal the square of the hypotenuse. That's how he would put it. Actually, this was known even before Pythagoras. See, the pyramids were put up between 6,000 BC and 3,000 BC. And when you're building something that size, it's kind of hard to make sure your corners are exactly square. So what the Egyptians would do is they'd take a rope, tie some knots in it at regular distances, and measure out a Pythagorean triple is what we'd call it. For example, 3 squared plus 4 squared, that's 9 plus 16 is 25, and that's 5 squared. So if you made sure that your rope was, here would be 4 cubits long, and here would be 3 cubits long, and this was 5 cubits long, and then you have 3 guys hold that tight, then you can be sure that this is a perfectly square corner. So this was known before Pythagoras, but he's the one who got his name on it. Actually, there are a lot of mathematical theorems that were known before their inventors were born. So chew on that, I don't know. But it's all about who popularizes it, who gets it into the books. But Pythagoras has his name on this contribution, so how can we relate that to this distance problem? Well, it's pretty simple. We're going to draw a right triangle over top of this picture. Going to go perfectly horizontal and perfectly vertical. As this was Descartes' contribution, as he realized horizontal distance and vertical distance are really easy. Now, what point is this? Well, it's straight up and down from 6, 4, right? It's straight up and down. So the x-coordinate is the same. The x-coordinates are both 6. And it's straight left and right. It's perfectly horizontal from 2, 1. So the y-coordinates both have to be 1. So this right here is the point 6, 1. Now we can do horizontal and vertical distances easy. From 2 to 6 is 4 units. And from 1 to 4 is 3 units. So this is actually the Egyptian triangle I was just talking about, 3, 4, 5. 3 squared plus 4 squared is equal to 5 squared. So this hypotenuse has to be exactly 5 units. If I hold up the ruler, that's going to be 5 units. All right, so you find those two distances, you use the Pythagorean theorem, you get your answer. Simple as that. Let's do another problem like this. Let's say this is the point. I don't know. Geez. I don't want the point to be the same. Let's say, how about -2, 1, And let's say that the other point is, I don't know, 0, 5. All right. So this point in the middle is going to be, what, 0, 1. It's nothing left or right, 1 unit up. Same y coordinate here, same x coordinate here. So this is a distance of 4, but now this is a distance of 2. Well, let's this unknown, let's call it c. 4 squared plus 2 squared equals c squared. That's 16 plus 4 is 20. So c is the square root of 20. And if you think way back to 1.3, we can simplify this a little bit. 20 is 4 times 5, right? So root 20 is root 4 times root 5, and root 4 is 2. So my final answer, I'm going to write it as 2 root 5. I could get this as a decimal with a calculator, but that would be less informative, actually. See, the thing is that the square root of 5 is irrational. It can't be written as a fraction, is what that means. Ratio, fraction. So rational is a fraction. Irrational is not a fraction. That's why they call them rational expressions in that last chapter. So this is an irrational number, which means if I try to write it as a decimal, it goes on forever without repeating. If it goes on forever without repeating, then if I try to write it on paper, I have to stop at some point. I am losing information there. So the only way to keep all the information is to keep it in this exact form. And that means we're going to prefer exact forms as our answers in this class. I'd rather you give me the answer as an exact than as a decimal. All right, so that's going to be our final answer, 2 root 5. Now, you might be saying, hey, wait, didn't you call this the distance formula? I don't recall you giving me a formula. To which I say, look, the Pythagorean method is really clean and easy. That's the way I'd prefer you to do it. But if you're the kind of person who likes memorizing formulas, and if you really want to brute force your way through this syntactically, okay, we can work this out. Let's say that this point is, because you should at least see this formula. Everyone else loves it. I don't, but let's say this point is xy, and this point is x. Okay, problem 1, these look the same. What I'm going to do is give them subscripts. This is a way to reuse a letter and have it mean a different thing. This is going to be x1, y1, and this is going to be x2, y2. Okay. All right. So what's this? This is a y distance. This is the difference, y2 minus y1. And this is the difference, x2 minus x1. Let's call this distance c. All right. Well, I know, dang it. I know that c squared is going to be the squares of the two legs added together. So it's going to be x2 minus x1 squared plus y2 minus y1 squared. Now, if I want to get c by itself, what I'm going to do is take the square root of both sides. So get rid of that squared. I don't have to worry about a plus or minus because I know these are always positive. So this is your distance formula. If you want to look at this as a formula, this is the way it goes. Like I said, I prefer just thinking of it as the Pythagorean theorem because this is kind of sloppy and hard to remember. I have a lot of students who will go into a test situation like, wait, was this a plus or a minus? Was this a plus or a minus? I don't remember. If you think of it as triangles, you don't have any of that problem. That's why I like semantics over syntax. How do I memorize this? I don't know. How do I memorize this? It's really easy. Let's take a look at how this problem would have looked if we had tried to do it the formulaic way. All right, it's going to be the square root of, what are my x coordinates? 6 and 2, so 6 minus 2 squared. And what are my y coordinates? 4 and 1, so 4 minus 1 squared. So that's the square root of 4 squared plus 3 squared. That's 16 plus 9. That's 25, and the square root of 25 is 5. So like I said, math is consistent. You get the same answer either way, but man, this feels better to me. If you really like this, please feel free to use it. I'm not trying to yuck anyone's yum, but I don't care for it. So that's the distance formula. Other thing is the ancient Greeks had a thing they loved called a midpoint. Whenever you draw a line segment, which is just a part of a line between 2 points, the midpoint, man, do I have to, you can guess, right? It's the point exactly in between them. Now, if we apply Descartes' invention, that midpoint, look, if these are the x coordinates, this guy right here is going to be halfway in between them. I'm going to take the average. Do you remember how to take an average? You add your two numbers together, and you divide by 2. Y coordinates are the same way. Oh, I drew these two close together. If this is y1 and this is y2, the average is y1 plus y2 divided by 2. So that's how you find the midpoint. If I want the midpoint of, I don't know, 3, 7, and 9, 1, halfway between 3 and 9 is 6, halfway between 7 and 1 is 4. Easy as that. Because 3 plus 9 divided by 2 is 6, 7 plus 1 divided by 2 is 4. Or you can think of a number line in your head and say, if I have a 3 here and a 9 here, what's halfway in between? Go 3 up, and I get 6. Go 3 more up, and I get 9. So either way you want to think of it. But that's midpoints. And that's all for 2.1. Join me next time for lines.